few examples to finish up from last time. We learned about a new thing called L'Hopital's rule. So, last time, forever ago, we learned about something called L'Hopital. So it says if we have a limit of f divided by g, and this approaches 0 over 0, or infinity over infinity, then this limit will be equal to the limit that you get by taking the derivative of the top over the derivative of the bottom. As long as the right one exists, the left one will also exist, and they'll always give you the same answer. So that's called L'Hopital's rule. And a bunch of examples, which I believe we did A, B, and C. So now I think we have those. So let's finish these guys up. See what else can help us out here. Move on. So D. Limit as x approaches 0 from the right of x to the x. Right. Ideas? Yeah?
Should we make it x to the negative?
Okay. So how is that helpful?
Because then when you derive it, it's like 0.
Why would you derive it? Because, I mean, as written, what does this approach, what does this look like? Well, the top is 1, right? And the bottom, you actually don't know what the bottom would be. Which means this isn't helpful. So rewriting it that way is not very useful because your top is 1. You need the top to be something that approaches 0 while the bottom is approaching 0, or the top is approaching infinity while the bottom is approaching infinity. But yes, of course, we need a way to actually get this to look like a division of some sort. A division that behaves like this under the limit. Ideas?
Can you use like a log or something?
How do you get a login? Yeah?
X, ln of x. So the x minus the front, and then I just did ln.
Yeah, but how do you even get the ln there in the first place? I remember you can't just introduce something without there being repercussions, right? But a log is a good idea because we have a power here in play. So you remember when we wanted to differentiate x to the x? We're like, oh, the power makes it complicated. Let's put a log in there. But we didn't just like randomly throw a log in there. There had to be some sort of process that allowed us to do this legally.
You said equal to y. Y equals.
Right, because then if I have an equation, I can log both sides of an equation. If I just have something here, I can't just throw a log in there. It's going to be different, right? If I have the number 2, I can't just suddenly go log 2. right? That's a different number now. I'm changing the value of what I'm looking at. So I need to find some way to get a log to help me out legally. So one way to actually do that is just, you know what? Set y equals this limit. And let's log both sides. Now, there's something that I mentioned with limits a while back, which might have been a little bit glossed over, but it's an important thing that's going to help us out in this case, is that limits can pass through continuous functions. Which means, because I know that the logarithm is a continuous function, I can literally shift the limit inside and outside of that at will. So I can actually move the limit part to the outside. And I can do that since ln is continuous. So this allows me to get an ln into play when I didn't have it before, but notice now I have an equation. There's an ln on the other side that I'm going to have to deal with eventually. So now this allows us to look at x ln x. Can I actually do that limit? Like if I were to plug in, what does this limit approach? 0 times negative infinity, which is an indeterminate form, but not one of the indeterminate forms I need. What do we do now?
You have to rearrange it. So ln of x over 1 over x.
This is in fact one of the earlier examples. I believe this was example C, right? So we kind of we've seen what to do here. Didn't want to introduce too many new things all at once. So I want to introduce the concept of logging both sides of a limit. Notice that it now puts us in a position where we can get to that division thing happening, which this now approaches infinity over infinity. Sure, it's negative infinity over infinity, but the sign doesn't matter here. But that now puts me in a position where I can apply L'Hopital's rule. So this implies that my ln of y is going to be equal, by L'Hopital's rule, to the limit that is obtained when I differentiate the ln and I differentiate the 1 over x. This is equal to, just simplifying here, minus x, which we now know that is 0. So the original limit is 0. Is that the answer? Right, so no. The limit is not 0. The ln of the limit is 0, which means what is the actual limit? How do I solve for y?
Y prime for y.
No, we're not differentiating. That's literally an equation where I want to solve for y. Yeah,
Would it be 1?
how do you get that?
Because e to the 0 equals y.
Right,
So
e both sides. You need to remember that for the test. I actually asked you to solve exponential and log equations on the test. So you need to remember all those things. You need to get rid of a log, use an exponential. So you e both sides, so your y is now equals e to the 0, which is 1. So that's actually your limit. The limit of this is actually 1. 1 is the answer. And again, I didn't just randomly throw an ln in there. I created an equation and logged both sides. That's how I can get the ln in there legally. But of course, once I actually get to an answer, I have to correct that ln that I threw in there by using an exponential to undo the change. And so yeah, that limit actually approaches 1. So I mentioned how the kind of techniques we use for log differentiation can be convenient here, and this is an example that shows how such a technique can be convenient. So sometimes you have something to a power, get a log in there, bring the power down. Once it's a product, you can either shift one of the things underneath by just taking the negative of the power and moving it to the bottom. So it's easier to go from a product of things to a division of things than it is to go from something raised to a power to a division of things. the log allows us to do that. So that would be, do that one. Okay, so for E, now that we've seen that technique, how do you think E is gonna work out? I wanna do the limit as x approaches infinity. Yes? Yeah?
Would you set it to y and then
Then?
then you bring, or then you would log both sides, so ln y equals ln x which is infinity. And then you bring down that, or bring the limit to the outside, and then bring down x.
And all of this. Now what?
And you multiply by 1 over x so that the x is like in the bottom.
What do you mean multiply by 1 over x?
Within the limit. Or sorry, divide by 1 over x. Because it's the same as multiplying by x.
So you can bring the x in the bottom. Now, technically before that, what you wanted to do is check what kind of limit you have just with the log there. Because a lot of times, the log will actually simplify things, so even at this stage, you can actually make a conclusion. But at this point, if you let x approach infinity, what would actually happen? Well, the x would approach infinity. And the ln of this guy would approach what? Well, as x approaches infinity, 1 over x will approach 0. So the this will approach ln of 1. ln of 1 is actually 0. So you have infinity times 0. So at this point, you realize there's an indeterminate form. And so now you know, okay, there are two convenient indeterminate forms. That's not one of them. Now I get the idea of trying to move one into the denominator. And by doing this, as x approaches infinity, the top will now approach, right? The 1 over x is going to approach 0. So the top will approach ln of 1, which is 0, over the bottom, as x approaches infinity, 1 over x will also approach 0. So now you have a 0 over 0 limit. And this means l'hôpital is good. You have to say it in a slightly French accent, or it won't work out. L'hôpital. Okay, so, all right. Now comes down to your derivative skills. How do you differentiate log of 1 plus 1 over x?
Negative x, -2, over 1 plus 1 over x.
Okay. And then how do you differentiate 1 over x?
Negative x, negative 2 negative.
Now, in general, here's the thing. After you apply L'Hopital's rule, you always try to simplify right after applying L'Hopital's rule. Now, there are problems where you can repeatedly apply L'Hopital's rule. Now, what you would notice here is if you let x approach infinity at this point, you would get 0 over 0 again. And someone might think, oh, do I need to apply L'Hopital's rule again? The problem is, you don't really know if you need to apply L'Hopital's rule again until you simplify. It's going to be to your benefit to actually simplify first, because this is one of those problems, you can just keep doing L'Hopital's rule forever, and you're always going to end up with a 0 over 0. But if you just take a second to simplify, it actually will work out a little bit nicer. So here, this is pretty much, I have, in the top, it's minus 1 over x squared over 1 plus 1 over x. And in the bottom, I have minus 1 over x squared. So I can do a keep, change, flip kind of thing. So that's x squared over 1. What's going to happen is the x squares are going to cancel, the negatives are going to cancel. So I can simplify this entire thing to become 1 over 1 plus 1 over x. So rather than having this complicated expression, I have a nicer expression to worry about. And now I'm thinking about this limit. As x approaches infinity, do I know what that's going to be?
What do you mean?
What this answer?
Oh.
Is this something I know? Limit as x approaches infinity of this expression. Yeah?
Is it 0?
How is it 0?
Because if you plug in infinity 1 over infinity is 0.
Yeah, but where does that apply? Where does that apply though? Where do you have 1 over infinity?
In the denominator?
So the denominator is infinity? As my x goes to infinity, what's going to happen in the denominator?
It's going to get smaller.
The entire denominator or
Just that part.
which part?
The 1 over x part.
Okay, so the 1 over x part is going to be doing something. What is it going to be doing?
Going towards 0.
That's going towards 0. Okay? So now, what is the overall thing doing?
Going towards 1.
It's going towards 1. Right? So you be very careful of what you're looking at. Right? So this part here approaches 0, not the whole thing. Right? As my x goes to infinity, the 1 over x goes to 0, but there's still a bunch of other things around. Like, the overall answer could never be 0 because the numerator is 1. A fraction with a numerator of 1 can never be 0. Because a fraction can only be 0 if the top is 0. So this actually approaches 1. So I guess the answer is 1? It's the same thing. Remember on the other side, and if you tend to be someone who would forget that you have to do something else, I would highly recommend just write it down every single time, so you're never going to forget it. So the log of the limit that you want is 1, which means, how do I get to the limit? E both sides. So y equals e to the 1. So that's actually e. And by the way, I did mention before that this is a definition of e, so you could actually just know that that was e from the very get-go. But here's one way you could prove it, using L'Hopital's rule to help us out. Repeat that. So very common technique, you're trying to find a limit, but there's like some power that you have to worry about. Well, logs deal very nicely with powers. Introduce a log. How do you do that? Well, you can set both sides equal to the thing, to set y equals the thing, and then log both sides, and that's one way to do it. That being said, you could also apply the alternative that I mentioned last time. Instead of doing log differentiation, you could have done just write this as e to the ln of x to the x. That would still work. And this would be e to the x ln x. And again, limits pass through continuous functions, so you have e to the limit of x ln x. And we computed this guy before, that was 0. And so you could get 1 right away without having to go. But again, that's personal preference. Either one of these methods will work. So you can separately set it y equals log both sides and blah, blah, blah. And you have to remember to undo the log at the end. Or you can just write the thing as e to the ln of the thing and do all that stuff in the power. And the e will always be there, so you'll never forget to apply the e at the end. Yes?
Could you just explain like the algebra of multiplying that by the negative x squared over 1?
Oh, because moving from here, right? So if I have this, what I do is this x to the minus 2, I instead write it as 1 over x squared. The same thing down here, I instead write it as 1 over x squared. So then I have this fraction divided by this fraction. And we know to divide a fraction by another, you take the bottom one, you flip it, and then you multiply. So that's what I did here. So this minus 1 over x squared now flips and becomes minus x squared over 1. So that's where this part comes in. And then this part is from the original too. So I just rewrote the x to the minus 2's as fractions. And then I took the bottom fraction, flip and multiply. That allowed me to get here. Ideas for this one?
Is it equal to y?
Why?
So then we can log both sides?
What would the benefit of that be? If you were to log e to the x minus x, how does that help you? Now, the log is a powerful thing, but remember, there are certain rules that govern how we can use it. In particular, do we have a rule that talks about the log of something plus something?
Log of a times.
No. What is the log of a times b?
Oh, it's the ln of a plus ln of b.
Ln of a plus ln of b, right? So if I have two separate logs being added together, I can actually combine them by doing a product, or vice versa. If I have a log of two things being added together, we don't have a rule for that. So you might be tempted to just ln the whole thing, but notice that this is something plus something else. The ln doesn't actually simplify that. So immediately jumping to the ln isn't the thing you want to do here. So first thing you want to do is kind of want to just assess what this limit would look like. As x approaches infinity, what would the e to the x approach? Infinity. What would the x approach? Well, infinity. So this is an infinity minus infinity limit. That is an indeterminate form. So the first thing I want to do is find a way to actually write that, if possible, as say a 0 over a 0 form or infinity over infinity form. When is a logarithm useful is if I have a power to deal with. I don't really have a power I want to deal with here. I have a subtraction I want to deal with. So probably how you'd want to go about turning a subtraction into a division, that's hard to do in general. The easier way to do it would be turn it into a multiplication first, then you can move one of the factors down in the denominator, if necessary. So how do you turn a sum of things into a multiplication of things? It's a general concept question. Huh?
Multiplication to addition. But we can, never mind.
No, I mean like, if I have a sum of things like an A plus a B, is there a way to write that, say, as something else, like a C times a D? Is there a process that allows me to make that kind of jump? Because I don't have the ln here. The ln of the sum isn't going to help me, so I'm not even thinking of an ln rule. Is there some other general idea, principle? How can go from a sum of things to a multiplication of things? Think of all the things where you can go from sums to products. It's really basic. You're going to kick yourself when I tell you what it is.
Is it factoring?
Factoring. That's exactly what factoring is, isn't it? Right? If I had like an x squared minus a 4, how can I write that as a product? X minus 2 times an x plus 2. I went from a situation where I had things being added to a situation where I have things being multiplied. Or if I had x squared plus 2x plus 1, I can bring that to a situation like this. Right? I can go from a thing where I'm being adding a bunch of things to a thing where I'm being multiplying a bunch of things. That process is called factoring. That's exactly what factoring is. Okay? So you have all these rules, but it's knowing the rules by heart is also important, but knowing when they would be useful to apply is going to be also nicer. I know I can get from a situation of multiplication to a situation of division pretty easily, but if I have a sum, how do I get to the division? Well, the first thing would be get to the multiplication, then go to the division. Well, how am I going to get to the multiplication? Factoring is how you get to the multiplication. That's what factoring is all about, taking a sum and writing it as a product. So, that would be the trick. The trick here is not to apply the ln. The ln is not useful in this case. The trick here is to factor. Can actually write this sum of things as a product of things. What do you want to factor? No common terms. Factoring is a little bit more general than that. So essentially, common terms is the easiest way to factor things nicely, but in general, you can factor out pretty much anything you want to factor out of something, as long as it's not 0 itself. So you can't factor out 0, but you can pretty much factor out anything else you feel like. So, for example, I see this expression, I can just decide, you know what, I want to factor x out of this expression, right? This is something that's doable. What would be left inside if I factor x out of the expression? Yeah?
Would it be e to the x over x minus 1?
E to the x over x. This one, right? Basically what factoring is when you pull something out, you kind of divide everyone inside by it. This was one of the things that were going on in the background. So if you had like x cubed plus x squared, we all kind of, automatically know that this factors into x squared times x plus 1. But the idea was, why does that factor into x squared times x plus 1? Notice what you actually did is you factor out an x squared, and how did you fix everything on the inside? Well, you divided everyone inside by x squared, right? It's kind of like you're multiplying and dividing by x squared at the same time. Notice now inside, this guy cancels, becomes 1. This guy cancels, becomes x, right? So the whole time when you were factoring, that's actually what you were doing. You pulled something out, you divide everyone inside by it. And so it turns out, because the bases were the same, it equated to you subtracting all the powers, and that's how you come to know about factoring. But in general, factoring is something that you can do with anything. Just pull it out and divide everyone by that thing that you pulled out. That's factoring. Now if I look at this guy, what does this look like? So as my x approaches infinity, now I have these two guys to worry about. What does the first guy approach? Infinity. Times, what does the second guy approach?
Infinity over infinity.
Infinity over infinity. So what would I be able to do here?
That's 0 minus 1, so then it's negative 1.
Well, how did you get that this was
Oh.
0?
Because infinity over infinity is. Oh, but then you said some infinities are greater, like.
Right. Infinity over infinity is an indeterminate form. Like you don't know what that is. You can do L'Hopital's on this part. But luckily for us, that was like example B. I think we actually did this specific problem earlier. So technically what you will do here is if you've never seen it before, what you would have done is you would apply the L'Hopital's here, because that gives you infinity over infinity. Differentiate the e to the x, differentiate that one, you get e to the x over 1. So this part actually goes off to infinity. So this term here will go off to infinity minus 1, which is infinity, still infinity, right? Now, what is infinity times infinity? Infinity squared, which is what? Infinity, right? So this is actually not indeterminate. This we can determine, not indeterminate. So we actually, the answer here is infinity. Right? Because you have a big number times a big number. What's that going to result in? A big number. Right? So that's actually not indeterminate. We actually know. Infinity times infinity is infinity. That's a thing. Infinity times 0, that's a problem. Because then you're like, well, if I multiply by 0, I should get 0. But if I multiply by infinity, I should get infinity. Which one? Like when there's a conflict, that's when you get an indeterminate form. Because you're just not sure. If you were to apply different math rules to the same thing, you get different answers. That's why it's kind of, I don't know how this is going to go. But this is pretty clear where it's going. It's getting bigger. So not indeterminate. So that is actually infinity. So in other words, the infinity in the first situation is much bigger than the infinity in the second situation. So these two infinities here are different somehow. The exponential infinity grows faster than the polynomial infinity. So we have a really big number minus another really big number, but just compared to this big number, that number is really small. Don't worry about it. But that's basically the idea. So here, again, we have a subtraction of terms. So you might want to try to figure out, and the tops are 1s, so you know that it's not going to be a 0 over 0, infinity over infinity. So now you want to think of ways that how I can turn this thing into something more usable. Because these guys each individually approach 1 over 0, which was nothing. So now, what we want to do, I mean, you can actually think of a little bit more nuance than that. This is actually approaching 1 over 0 plus. So technically this is approaching infinity as I'm going to 1 from the right side. So, and then this, if I'm going to 1 from the right side, 1, so this is again 1 over 0 plus. It's another infinity minus infinity actually. If I just had a 1 here, then does not exist would be the answer. But I have 1 from the right, which actually gives some semblance of meaning. But it's still, as a form, indeterminate. So the thing is, want to kind of create this into a product. Won't necessarily have to do something like this, but another nice thing to do is, if I have two fractions, why not just combine the fractions? That might be something that you kind of do. That will give you a division right away. So let's turn this into one big division by just adding the fractions. Of course, the quickest way to add fractions is to cross multiply the tops. To find the tops, x minus 1 times 1 is x minus 1 minus, put this sign back, ln x times 1 is ln x. And then you multiply the bottoms to get the new bottom, which is now x minus 1 times ln x. So that's the combination there. What you can also notice now is that, so this is limit as x approaches 1 of x minus 1 minus ln x over x ln x minus ln x. And what does that guy approach? Well, if my x is approaching 1, then x minus 1 is approaching 0, and ln of x is approaching ln of 1, which is also 0. So the top is 0. In the denominator, if my x is approaching 1, this part will approach 1 times ln of 1, which is 0, minus ln of 1, which is 0. So this is a 0 over 0 situation. That means you can apply the Euclid method. So, derivative of the top is what? Derivative of x is 1. Derivative of 1, 0. Derivative of minus ln x,
1 over x.
1 over x. Over, how do I differentiate the bottom? How do you differentiate x times ln x? Product rule. So? So?
ln of x plus 1, well, times 1 of x.
No. Write it out slowly then. So you differentiate the x, leave the ln.
Oh, x.
Then you leave the x, differentiate the ln. And so it's ln of x plus 1 minus the 1 over x. Right, so let's clean that up a little bit. So this is limit as x approaches 1, 1 minus 1 over x over ln of x plus 1 minus 1 over x. Now if I let my x approach 1, what's going to happen? So if my x approaches 1 for this guy,
Is it going to be infinity?
so if my x approaches 1, 1 over x is just going to approach 1, 1 minus 1, 0. In the bottom, if my x approaches 1, log of 1 is going to be 0 plus 1 is 1 minus 1 over x. Well, that approaches 1, so I get another 0 over, on the bottom. So it's again a 0 over 0. So what do? I look at that again. That was more Italian, wasn't it? Look at that. Yeah, I don't know what happens when you say it in Italian. You know, it could stop working. I don't know. It's a risk. Yeah, so I get 0 over 0. Now I'm going to do it again. Differentiate the 1. That becomes 0. Differentiate that. I get 1 over x squared. Differentiate the ln x. 1 over x. Differentiate that 1. Goes away. Differentiate this 1. I get 1 over x squared. So now, all the ln's are gone. At this point, I would like to simplify before I worry about trying to apply the L'Hopital again. So I'm going to multiply by x squared over x squared. That'll give me 1 over x plus 1. And now, let x approach 1. That's actually a nice answer. That's a half. Yeah, that limit, infinity minus infinity, it's actually a half. Right? It's like so random what something like that could be. Right? That's why it's indeterminate. It could be whatever. Like here we had an infinity minus infinity, the answer was infinity. Here we have infinity minus infinity, it's like a half. Like what the hell? Right? So like that's really indeterminate. There's no way you could predict that that would have been a half. Come on. Who would have guessed a half was the answer here? What's that? No, I guess we'll stop there. I mean, linear approximation would be the next thing I would talk about, which would give you the second bonus problem, but no point in rushing that in 5 minutes. So we'll stop there. Make sure you study, take the review as a test. It's up, and yeah, that should time yourself while during the review. Do it under test conditions, so that will give you a pretty good, accurate position of where you